What powers the future of our world? How will humanity move across continents, through cities, and into a cleaner tomorrow? The answer is not buried deep in the earth as fossil fuel. It is something we are building right now, a marvel of chemistry and engineering. It is the battery, specifically, the battery inside an electric vehicle. The quiet hum of an electric car is more than just a sound. It is the signature of a fundamental shift in how we think about energy, transportation, and our collective impact on this planet. This transition, from the roar of internal combustion to the silent surge of electric power, is one of the great technological stories of our time. Electric vehicles, or EVs, are rapidly becoming a common sight on our roads. But the real magic, the true revolution, is happening out of sight. It is a complex dance of ions and electrons. This battery pack is not just a component. It is the very heart of the machine. To understand the future of mobility, you must first understand the science of the battery. Let's embark on a journey into this incredible technology. We will start with the batteries that power millions of EVs today. The story of the EV battery is a cosmic tale in miniature. The lithium that powers them was forged in the Big Bang and in the hearts of dying stars. We are now learning to arrange these ancient elements into structures that can power our modern lives. The journey from a simple concept to a sophisticated, intelligent power source is a testament to human ingenuity. So let us begin our exploration, starting with the chemistry that makes it all possible, the lithium-ion batteries of today. At the core of nearly every electric vehicle on the road today is the lithium-ion battery. This is the same fundamental family of technology that powers your smartphone and your laptop, but scaled up and engineered for the immense demands of transportation. Think of it not as one giant battery, but as an orchestra of thousands of individual cells working in perfect harmony. These cells are managed by a sophisticated computer, the Battery Management System, or BMS, which acts as the conductor, ensuring every cell is performing safely and efficiently. Within this family, two main chemistries have emerged as the leaders in the automotive world. The first type is LFP, which stands for lithium iron phosphate. Imagine this as the sturdy, reliable workhorse of the battery world. Its greatest strengths are safety and longevity. LFP batteries are chemically very stable, making them highly resistant to overheating, which is a critical safety feature. The second prominent type is NMC, which stands for nickel manganese cobalt. If LFP is the workhorse, think of NMC as the long-distance runner. Its key advantage is its higher energy density. This means an NMC battery can store more electrical energy in the same amount of space and weight compared to an LFP battery. However, the inclusion of cobalt and nickel makes these batteries more expensive and raises important questions about the ethical and environmental sourcing of these materials. The size of the battery pack, measured in kilowatt hours, directly determines how far an EV can travel on a single charge. Think of kilowatt hours as the size of the fuel tank. A smaller, more affordable city car might have a 30 kilowatt-hour battery, offering around 250 kilometers of range, which is more than enough for daily commutes. A larger, long-range luxury sedan might boast a 100 kilowatt-hour pack, capable of traveling over 600 kilometers. Automakers must carefully balance battery size with the vehicle's cost, weight, and intended purpose, creating a diverse range of options for every type of driver and need. To truly compare and understand EV batteries, we must look beyond their chemical names and delve into three fundamental concepts. These are the pillars that define a battery's performance and determine its suitability for a given application. The first, energy density, is perhaps the most talked about metric. It refers to the amount of energy a battery can store relative to its physical size, volumetric density, or its weight, gravimetric density. A higher energy density means you can pack more range into a car without making it bigger or heavier, which is the holy grail for automotive engineers. Next is cycle life, which defines the battery's longevity. One cycle represents one full charge and one full discharge. The cycle life tells you how many of these full cycles a battery can endure before its capacity degrades to a certain point, typically 80% of its original state. A battery with a high cycle life will serve the vehicle's first owner for many years and may still have enough capacity for a second life in a less demanding role. LFP batteries are champions in this regard, often capable of thousands of cycles, which contributes to a lower total cost of ownership over the vehicle's lifespan. Safety is, without question, the most critical pillar. All the range and longevity in the world mean nothing if the battery is not fundamentally safe. The primary concern is an event called thermal runaway. This is a chain reaction where a single damaged or defective cell overheats, causing neighboring cells to overheat as well, potentially leading to a fire. Modern EV batteries are designed with multiple layers of safety systems to prevent this. This includes robust physical casings, advanced cooling systems using liquids and air, and the ever-watchful battery management system, which constantly monitors temperature, voltage, and current to keep everything within safe operating limits. Finally, we must consider the flow of energy, charging. There are different levels of charging, each suited for different situations. AC, alternating current charging, is the slow and steady method, perfect for overnight charging at home or during the workday at the office. DC, direct current fast charging, found at public stations, can replenish a significant portion of the battery's range in under an hour. The newest generation, ultra-fast charging, aims to add hundreds of kilometers of range in just 15 to 20 minutes. However, pushing electricity into a battery, this quickly generates immense heat, requiring sophisticated thermal management to protect the battery's health and ensure its long-term durability. While today's lithium-ion batteries are technological marvels, they are not without their challenges. The most significant barrier to mass EV adoption has been cost. Battery packs used to be nearly half the price of an EV. The good news is that this cost has been falling dramatically. 2010, around $1,200 per kilowatt hour. 2025, approximately $130 per kilowatt hour. That decline is making EVs competitive with gasoline cars, and the trend should continue. Another major consideration is the environmental and ethical impact of mining raw materials: lithium, cobalt, nickel. Mining can be water-intensive and disrupt local ecosystems. Cobalt sourcing has raised ethical labor concerns in some regions. Industry response: moving to low or no cobalt chemistries. Industry response: creating transparent, sustainable, and ethical supply chains that protect people and the planet. Range anxiety: the fear of running out of power before reaching the next charging station, often psychological for daily use, real for long trips. Solving it needs a reliable, widespread public charging network. Batteries are sensitive to extreme temperatures. In very hot climates, like parts of India, heat speeds up battery degradation unless cooled. End of life. What happens after a decade of service? You can't just landfill batteries. They're hazardous and valuable. Solution: a circular economy. Step 1, recycling to recover lithium, cobalt, nickel. Step 2, second life use. Second life example, backup for home solar. Second life example, helping to stabilize the electrical grid. The future of electric vehicle batteries is incredibly bright. The most anticipated of these is the solid-state battery. In today's lithium-ion batteries, the energy flows through a liquid or gel-like substance called an electrolyte. Solid-state batteries, as their name implies, replace this liquid with a thin, solid material, ceramic or polymer. This seemingly simple change has profound implications. For one, it dramatically enhances safety. Solid electrolytes are not flammable and do not leak, virtually eliminating the risk of thermal runaway. Beyond safety, solid-state technology promises a monumental leap in energy density. Early research suggests solid-state cells could store nearly twice as much energy as today's best NMC batteries of the same size and weight. This could mean EVs with a range of over 1,000 kilometers on a single charge, or smaller, lighter, more affordable cars with today's standard range. Furthermore, they are expected to support incredibly fast charging speeds, potentially allowing a driver to add hundreds of kilometers of range in the time it takes to grab a cup of coffee, perhaps just 10 to 15 minutes. While challenges in manufacturing costs and durability remain, major automakers and startups are racing to bring this technology to market within the next decade. While solid-state gets much of the attention, other chemistries are also showing great promise. One exciting alternative is the sodium-ion battery. Sodium is one of the most abundant and inexpensive elements on Earth. Think of table salt. This makes sodium-ion batteries potentially much cheaper to produce than their lithium-based cousins. While their energy density is currently lower than LFP or NMC, making them less ideal for long-range performance cars, they are an excellent candidate for affordable city EVs, two-wheelers, and large-scale stationary energy storage. Several manufacturers, particularly in China, are already launching the first generation of vehicles powered by sodium-ion packs. We must also mention hydrogen fuel cells, which offer another pathway to zero-emission mobility. A fuel cell vehicle is technically an electric vehicle, but instead of storing electricity in a battery, it generates it on board by combining hydrogen gas with oxygen from the air. The only byproduct is water. Their main advantages are long range and rapid refueling, which can be done in about 5 minutes, similar to a gasoline car. While hydrogen infrastructure is still in its infancy, and the technology is currently more expensive, fuel cells are seen as a very promising solution for heavy-duty long-haul trucks and buses, where battery weight and long charging times are significant obstacles. The transition to electric mobility is not happening in a vacuum. It is a coordinated global movement driven by policy, innovation, and a shared vision for a sustainable future. In Europe, ambitious targets have been set, regulations aiming for a complete phase-out of new internal combustion engine car sales by 2035. In the United States, massive investments are being poured into building a domestic supply chain, new gigafactories for battery production sprouting up across the country. This localizes manufacturing, reduces logistical costs, creates a new generation of high-tech jobs, securing the nation's role in the future of transportation. This movement is also gaining powerful momentum in India. The government's production-linked incentive schemes are actively encouraging domestic and international companies to manufacture batteries and electric vehicles within the country. This policy fosters self-reliance and positions India as a key player in the global EV market. The recent discovery of significant lithium reserves in Jammu and Kashmir could further bolster this domestic push, potentially reducing reliance on imports. Indian automakers have wisely leaned into LFP battery chemistry for their mass-market cars and two-wheelers, a choice perfectly suited to the country's climate, road conditions, and consumer demand for durable, cost-effective solutions. Looking ahead, we can make a bold prediction. Driven by manufacturing scale, improving chemistry, and smarter design, the cost of battery packs is projected to fall below $70 per kilowatt-hour by 2030. At that price point, the upfront purchase price of many electric vehicles will achieve parity with, or even become cheaper than, their gasoline-powered equivalents. When you factor in the lower running costs and reduced maintenance, the total cost of ownership will become overwhelmingly favorable for electric. This will be the tipping point that accelerates mass adoption across the globe. The battery is also becoming smarter. Future EVs will feature AI-powered battery management systems that learn your driving habits to optimize performance and extend battery life. Wireless charging will allow you to simply park your car over a pad to recharge, eliminating cables entirely. And with vehicle-to-grid technology, your car will become part of the energy solution. It can store cheap renewable energy during the day, sell it back to the grid during peak demand hours, stabilizing the power supply and even earning you money. Your car will no longer just be a mode of transport. It will be an active, intelligent node in a cleaner, more resilient energy network. The question is no longer if this future will arrive, but how quickly we will embrace it. Are we ready to adapt?